That sounds horrible.
Okay, so what I want to do today is, in fact, do a little bit of topology, okay? So we're going to make a little digression here. So, topology. Don't freak out, this is not going to be a course on topology, okay? But these are ideas that will help us, the way I'm going to define limits, continuous functions in terms of these topological ideas, and that generalizes in an easier way for when you, for other types of spaces other than real numbers, okay? So my first definition would be the following. First of all, let me remind you that when we have this notation V epsilon of C, by that we mean the set of all real numbers x such that the absolute value of x minus c is less than epsilon. And this is called the epsilon neighborhood of the number c. So here c is a real number. So what this is really is what? This is just a open interval centered at c of what's the length of that open interval? The length of that open interval is 2 times epsilon, right? I mean, you have an interval, is c minus epsilon to c plus epsilon. So it's an open interval centered at c of length 2 epsilon, right? And another concept that I want to introduce here is if we write the same thing V epsilon of c, okay, but I'm going to put a line on top of V, that would mean the set of all x in R such that 0 is less than the absolute value of x minus c is less than epsilon. And if you notice, what's the difference between these two sets? Well, the only difference is I'm saying that the absolute value of x minus c is greater than 0, which simply means that I don't want to take x to be c. Okay, so you're taking the same, so this is actually the same as the epsilon neighborhood of c, except that you're getting rid of the point c. Okay? So this is called the deleted epsilon neighborhood. This will be called the deleted epsilon neighborhood. So here's how the picture looks like in this case. It's going to be c minus epsilon, and the c is excluded, and here is c plus epsilon. And in the first case you have c minus epsilon and c plus epsilon, and c is also included. Is that making sense? So that's the only difference between the deleted epsilon neighborhood and the epsilon neighborhood of c. Okay, is that clear? You guys are okay with that? Okay. Here's my next definition. So another definition. So this definition is, I think I have already talked to you about the cluster points. Okay, let me move on to then the definition of an open set. a subset A of the reals, a subset of real numbers is said to be open, is said to be an open set, is said to be an open set in R if for each x in A, for each x inside of A, there exists a neighborhood, there exists a neighborhood V epsilon of x entirely, there exists a neighborhood of x entirely contained in A. Let's see if it makes sense. Okay, I'm saying that a subset A of R, it's open in R if for every x in A there exists a neighborhood of x which is entirely contained in A. Is that making sense? So for every x in A, you can find an interval centered at x such that that interval is also entirely contained in the set A. Okay? And I'm going to give you a few examples in a bit. But we also have this notion of a closed set. So a subset A of the reals is closed, is a closed set in R. It's closed if its complement in R, which is the set from the set of reals, you take out A. If its complement in R is open. So we are going to call A to be a closed set if its complement, that is all the real numbers outside of A, that set of real numbers, if that set of real numbers is open, then we say that A is closed. Okay. All right, so now let's go over a few examples of open and closed sets. My first example, let's look at the set A to be the set 1 and 2. The question is this set open or closed? Okay, is this set open or closed? Now remember, open means given any number in my set A, it has a neighborhood entirely contained in the same set, right? So there are two numbers, right, 1 and 2. So is this set open? Well, you have to see, well, if I pick the number 1, does it have a neighborhood entirely contained in the set? Well, obviously no, right? It just contains 1 and 2. So if I pick, there is no neighborhood of 1 which is entirely contained in that set. Same for 2, right? So it's not open. Not open. Now, the question is this closed, however? Is this a closed set? What would you say? What's the definition of a closed set? We say that A is closed if its complement is open. Well, what's the complement of the set A in R? Except 1 and 2. Now, is that set open? That is, you have to ask yourself, given any number other than 1 and 2, okay, can I find a neighborhood of that number which is entirely contained outside of A? Is that true? Yes, obviously it's true. So it's not open, but it's closed. And in fact, this is the same thing for any finite set, okay? So let A be any finite subset of the reals, then A is closed. Okay? 3, if I take the set of all natural numbers, right? The set of all counting numbers, do you think it's open or closed? First of all, is that open? No, okay, and is that closed? That is, if you look at its complement, would be all the real numbers except for the counting numbers. Is that set open? The complement of n, is that open? What did you say?
It's not open.
It's not open, yes. I'm saying, is it closed?
Oh, so it's the complement.
Is the complement open then? That's the question. If you want to show it's closed, you have to show its complement is open, right? So the question is the complement of n open? Yes, no? What do you have to answer? That given any number which is not a counting number, does it have a neighborhood entirely contained outside of n? Right? If you take any, yes, so it's closed. You guys are convinced with that?
Because like
Yes.
the complement would be
Mhm.
all the numbers between 0 and 1, all the numbers between
1 and 2 except 1 and 2. So any number you pick there, it's got to have a neighborhood
Right.
entirely contained in outside of n. Okay. Tommy, is that okay? All right. Another example. How about the entire set of real numbers? If I take the entire set of real numbers, what can you say? Is it open, first of all? Clearly open. How about, is it closed? How about the empty set? Is the empty set open? Yes, the empty set is also open. There is nothing there. The way you want to read it is that if you have a point in X, then it has a neighborhood which is entirely contained in A. The definition is, if X is in A, then it has a neighborhood inside of A. So if there is no X in A, then if it is empty set, then it's necessarily open, okay? So this is the empty set, so is the empty set. But, well, since the empty set is open, the empty set is the complement of R, so R is also closed, okay? R is also closed, as well as the empty set. Let me call that phi, so as well as the empty set phi. Everybody's okay? Okay, let's look at another example. 5. Remember in calculus we used to call intervals, this interval 0 to 1 to be an open interval, right? The word open, it's better be an open set, okay? 0, 1, is that an open set? Well, you have to ask yourself, given any number there, can you find a neighborhood of that number which is also inside of that set, right? And the answer is yes, right? Because 0 and 1 are not included there. So this is open. This is an open set. This is an open set in R. How about this? 0 to 1. With 0 and 1 included. Well, this is not open, right? This is got to be closed. it is closed because if you look at the complement of the set of all numbers between 0 and 1, including 0 and 1, that means you have all the numbers above 1, all the numbers below 0, excluding 0 and 1. Those are open sets, right? So this is a closed set.
So I have a question. If we
Yeah.
have a set
Mhm.
that is not open, is it necessarily closed?
If you have a open set,
Or we've got a set that's not open.
if it is not
Does that
open,
imply that it's closed?
does it? No, not necessarily. You see, the definition is, so when we defined a closed set, right, we said that if it is, if the set, I didn't say that a set is closed if it is not open. What I said, a set is closed if its complement is open. Okay. Here's another example, 7. Let's say I take the set of numbers from 0 to 1, but this is a half open interval, okay? So what is it? Is that open? Is that closed? You see, what this is basically a counterexample to what you suggested, okay? You said if a set is not open, is it necessarily closed, right? Well, this side, is that open? Well, it's not open because you cannot give me a neighborhood of 1. You can't give me a neighborhood of 1 which is entirely contained in that set, right? So this is not open. Not open in R. So what you asked me is, if a set is not open, is it necessarily closed? So you want to say, well, is this guy closed then? Well, you take the complement of that, right? If you take the complement, you get all the numbers below 0, excluding 0, and you get all the numbers above 1, including 1, right? So is that set open? Well, sorry, what I said, let me take it back. What I wanted to say, the complement has 0 in it, but 1 is not included. So since the complement has 0 in it, note that a neighborhood of 0 is not in the complement, right? So that is, what is the complement here? If I make a drawing of that, the complement looks like here is 0, and you get all the number to the left of 0, including 0, and then here is where you have 1, and 1 is not included, and all the numbers here are included, right? So maybe I'll just highlight this part here. Whoops. Let me just say this. Is that making sense? So 0 is included, 1 is not. So if it is open, then you gotta find a neighborhood of 0 which is entirely there, but it's not. So that means that 0, 1 is not closed either. Is not closed either. Did that make sense? Okay. Okay, so those are all the examples of what we mean, what are some open sets and closed sets. And what you saw was that there could be sets which are neither open nor closed. There could be sets which are both open and closed, like the set of all real numbers. Okay. All right, so here is a theorem. Here is the theorem. The union, so number 1, the union of an arbitrary collection of open sets in R. The union of an arbitrary collection of open sets in R is open. And 2, the intersection the intersection of a finite collection, the intersection of a finite collection of open sets in R is open. So the first one says the union of an arbitrary collection of open sets would be still open. If I take the intersection of a finite collection of open sets, that's also open. It is not true that if you take the intersection of an infinite collection of open sets, the intersection may not be open. Is that okay? Now you have corresponding statements for closed sets. Okay. The intersection of an arbitrary collection of open sets, sorry, not open sets, closed sets, is closed. Okay, and for the union of a finite collection of closed sets is closed. So whenever I'm saying closed sets, I'm talking about closed sets in R, of course. Okay. Instead of writing down the details of the proof, let me just discuss the ideas in the proof. So the first statement is what? The first statement is that if I take the first statement that I gave, it says that the union of an arbitrary collection of open sets in R is open, right? Well, let's just take an arbitrary collection of open sets. So let's take a collection, say I'm going to call them U alpha. So alpha belongs to a certain set, okay? It's just an arbitrary collection of open sets, and each U alpha is open in R, okay? So I'm taking an arbitrary collection of open sets, and we want to show that the union is open also, right? So let's take U to be the union. So the union of U alpha, and the union is over all the indices alpha, okay? You guys are familiar with this type of notations, right? Okay. So what is, I want to show that the union is open, right? So what do I have to show? Given any point in the union, it has a neighborhood inside the union, right? Well, suppose I pick X in U, right? If I pick X in U, if X is in U, then isn't that true that X belongs to some U alpha? Right? Well, U alpha is open, right? U alpha is open. So there is a neighborhood of X which is entirely contained in U alpha, since U alpha is open, right? Well, if since U alpha is open for some epsilon, of course, for some epsilon greater than 0. So there is a neighborhood of X which is entirely contained in U alpha. Well, then clearly that neighborhood is also inside the union, right? But V epsilon of X belongs to then the union U. Okay? So if given any, so what we have showed is given any X in U, it has a neighborhood which is entirely contained in U, right? Which means that U has to be open. So I could say that U is open. And I don't want to really prove the other ones. They are all the same, okay? The next one was the intersection of a finite collection of open sets in R is open, okay? And the third one was the intersection of, see, third one says the intersection of an arbitrary collection of closed sets is closed, right? What's the difference between 1 and 3? I'm talking about the union of arbitrary collection of open sets is open. Here I'm saying the intersection of an arbitrary collection of closed sets is closed, okay? Everybody's okay? So you take the arbitrary, if you take the reason 1 and 3 looks like this is because, remember, we defined a set to be closed if its complement is open, okay? Now, in number 3, whatever collection of closed sets you have, their complements are all open sets, right? And then you can take the union of all those open sets, right? So if you take the union of all the complements of these closed sets, you get an open set, right? And then the complement of that union would be closed. And that, in fact, would be the intersection. And that follows from what? Let me see. Let me just say maybe a few more words in this. Let's say number 3. So what I'm saying here is that we are taking an arbitrary collection of sets U alpha, and we are saying that U alpha closed, right? Each U alpha is closed in R. Okay? And we want to show that the intersection of U alpha is also closed, right? So what I'm saying, well, let's take V alpha to be the complement of U alpha in R. So you get rid of U alpha from R, that's the complement. So then V alpha is open in R, right? Remember, a set is closed if its complement is open, right? So V alphas are all open sets. So if I take the union of V alpha, right? If I take the union of all these V alphas, then the union is also open by 1, right? Now notice that what's going to happen if I take the complement of this set, that's union. So what I'm saying is that, so let's look at the complement. If I take the complement of the union of V alpha, I claim that's just the intersection. I claim that's just the intersection of U alphas. Let's see if you agree with that. What is that law known as? I think that was, you must have seen this law before. Yeah, I think it's called the De Morgan's law. Okay. So what we are doing is that we are taking the complement of the union, right? If I'm taking the complement of this union, then it will be the intersection of the complements of the individual. But the complement of each V alpha is U alpha, right? Is that making sense? The complement of each V alpha is U alpha. So De Morgan's law says when you take the union of when you take the complement of this union, you get the intersection of the complements of each V alpha, okay? But the complement of each V alpha is, of course, this guy. U alpha is the complement of V alpha. Did that make sense? And again, the other ones you can prove in a very similar way. I don't want to spend time on those. But what you have to remember is that an arbitrary collection of open sets is open. The union of arbitrary collection of open sets is open. The intersection of arbitrary collection of closed sets is closed. The intersection of a finite collection of open sets is open. The union of a finite collection of closed sets is closed. Okay, 4 things. Okay, so that's one of our main theorems here. Another theorem here. This is very interesting. Please ask questions if you have any. Let's let in this case that I have a subset F of the reals. And then the following are equivalent. Number 1. F is a closed subset of R. So F is closed in R. And number 2 says if Xn is any convergent sequence in F, then the limit of Xn also belongs to F. Let's see if you see what is the meaning of each statement. The first one says F is just a closed subset of R. And the second statement says that I have a convergent sequence where all the terms lies in F. Each term of the sequence lies in F. Then the limit of the sequence is also in F. Okay? So in other words, we are saying that F is closed if and only if every convergent sequence in F converges to a number in F. Every convergent sequence in F converges to some number in F. Okay? So that's the statement of this theorem. Okay. So how do we do this? Okay. How do we prove that that's the case? Well, let's show that 1 implies 2 first. Okay. So here's the proof. If I want to show 1 implies, so we're going to show 1 implies 2 first. So what do? I just assume that F is closed. So let's assume that F is closed. In R. Okay, and I have to show that if there is a convergence sequence inside of F, its limit is there, right? So let's take a convergence sequence. Let's let Xn be a convergent sequence such that Xn is in F for all n. Right? It's a convergent sequence inside of F, and also let x to be the limit. Okay, x is the limit. So what do I have to show? X belongs to f, right? Okay, so how do I know that x has to be inside of f? Anybody has any ideas on that? How do you show?
If it's a convergent sequence inside F, then it must
Mhm.
converge to something that's also inside F, correct?
That's what we are trying to show, that if you have a convergent sequence in f, and we have to show that it converges to something inside of f. That's what we are trying to show. So x is the limit of xn, then how do you argue that x gotta be inside of f? Of course, you gotta somehow use the fact that f is closed, right? That's the assumption here, the f is closed. So how do you argue that x is inside of f?
Well, if it converges to something outside of F, or if the limit is something outside of F, then
Well, let's think about it this way. I mean, if x is not in f, right, then x will be in the complement of f, right? So what would that mean? If x is in the complement of f, the complement of f is open. So x will have a neighborhood which is entirely outside of f. If x is not in f, an entire neighborhood of x will be outside of f. But x is the limit of xn, right? So no matter what neighborhood you pick, there's got to be some xn there, right? Is that making sense? So that's why x has to be in f. So so here's one way maybe we can write it down, that if let me say that suppose on the contrary, that x is not inside of f. Well, then there exists epsilon greater than 0 such that a neighborhood, the epsilon neighborhood of x is entirely contained in the complement of f, right? But there exists capital N such that for all n larger than capital N, right, xn is inside of the neighborhood, right? The epsilon neighborhood of x, right? But then we are saying that the neighborhood is entirely outside of f. However, it contains something from f, right? So that's the contradiction. This is a contradiction. And we are done. Okay? All right. So how about the other way around? Now you're going to assume that I have a convergent sequence. No. Now the assumption is that every convergent sequence in F converges to a point in F. That's the assumption. And you have to show that F is closed. So here now we show two implies one. So we assume every convergent sequence in F um, every convergence sequence in F, let me just say this, for every convergence sequence in F, the limit of, let me give it a name, xn. The limit of xn is in F. Every convergence sequence xn in F has limit in F. That's the assumption, and you want to show, we need to show F is closed. We need to show F is closed. Okay, anyone?
Could we, contradiction again, say F is open,
Okay.
and show that there are elements out there in the complement, such that that's what it implies, and then we're contradiction.
Well, you have to show that. If you're assuming, remember, if you're assuming that F is not closed, that doesn't necessarily mean that F is open. Remember, I had a set, the half open interval, which was neither open nor closed.
So should we assume that F is open then, and then the complement would be
Well, if you're trying to show that F is closed, so what is the definition of F being closed? Its complement is open, right? So basically you have to show that the complement of F is open. Okay, so if you want to show that the complement of F is open, you have to show what? Well, for every element in the complement, it has a neighborhood which is entirely inside of that complement, right? So how is that possible? You're going to pick X inside of R. You're going to pick X inside of the complement of F, and you want to show it has a neighborhood which is entirely outside of F. You have to somehow relate that to the assumption. The assumption is that every convergence sequence xn in F has a limit in F. Oops.
Yeah,
This one? Okay. Mm-hmm.
So we're gonna say that the limit of xn is in the complement of F. Is that what we're doing?
The way I was
Okay.
the way I was thinking was to
Yeah.
say that F is open, and then find a Y in the complement or X in the complement. Such that it's not
If you're trying to contradict, then you have to assume that F is not closed, right?
right.
Just
But-
not closed, not open.
Not closed, yeah.
Okay, so just not open.
But F not closed doesn't mean F is necessarily open, right?
Right.
But if you say that F is not closed, it means that the complement of F is not open.
And then,
And we can show that there's
Mhm.
if it's not open, then we find a neighborhood in the complement.
Okay, so let's say,
complicated.
so what do we have to show? We have to show, just write down, we have to show that the complement of F, if I take the complement of F, is open, right? That's what we have to show. Now, you're saying let's do a contradiction. You're saying, well, let's assume, suppose on the contrary, On the contrary, that R, from R, if you take out F, the complement of F is not open. So what's the meaning of that? What is the meaning of saying that the complement of F is not open? Remember, open means every element has a neighborhood entirely there, right? Every point has a neighborhood. So if it is not open, it means there's gotta be a point such that no matter how small neighborhood you pick, it always has something outside of that set, right? So this is what let's see if you agree that I can say that there exists X which is in the complement of F such that for any epsilon greater than 0, you know what, instead of saying epsilon, let me say it this way. For any n in n, for any n in n, the 1nth neighborhood of X, 1nth neighborhood of X, it's not entirely contained in the complement, right? Which would mean that it's gotta intersect the set F, right? It's going to be non-empty. Let's see if you agree with me. Tommy and CJ, you guys agree with that? That if I have, we are saying that if I assume that R/F is not open, it means that there's got to be something there such that no matter how small neighborhood you pick at that point, it's always going to intersect F because it's not entirely contained in the complement, right? Well, if you agree with that, let's see how we can define the sequence now. So what is the meaning of that? That means that for any n in n, there exists xn in F such that the difference between xn and x is less than 1 over n, right? You agree with that? Because what we said is that the 1nth neighborhood of X intersects F, right? So something in F must be in that neighborhood. So I'm saying let's call that xn. For any n, there is an xn in F such that xn is within 1nth of X, right? Well, then xn converges to what? Well, xn converges to X, right? Well, then I have a sequence xn, and xn converges to X. But then what's the assumption? The xn is a sequence in F, right? So what's the assumption? Any sequence in F converges to something in F, right? So by assumption then, by hypothesis then, X has got to be in F, right? Now where is the contradiction then? Where is the contradiction? We started with X outside of F, and then we are saying X is inside of F. That's where the contradiction is, okay? Contradiction. Contradiction. Okay? So that's the proof. So from now on, from now on we're going to say F is closed if and only if every convergent subsequence in F converges to something inside of F. Everybody's okay? All right, I think we are out of time. Long time ago. All right, next time we're going to finish this topological ideas and move on to chapter 4, okay? Now, my definition